This is a set of lectures and a short course in dimensional analysis. I have in mind a student who already knows some basic physics. In the first lecture, I'm going to give some ideas on the definition of dimension. In physics, whenever we talk about an observable, we mean it is measurable. Physics equations are formulas between these measurable quantities. When we measure an observable, we assign a number to it. Some observables have dimensions and some are dimensionless. We denote the dimension of the quantity x by bracket of x. For example, if x is length and t is time, then bracket of x is capital L and bracket of t is capital T. Here, length and time with dimensions L and T are taken as independent dimensions. Dimension of velocity is L over T or L T inverse, and it is a dependent dimension. The numerical value of each dimensional quantity depends on what system of units we choose. When replace the system of units, the assigned number to the dimensional observable may change. For example, when we replace the length unit from meter to centimeter, all quantities whose dimension contains length will change. The numerical value of any dimensionless quantity is the same for all system of units. Every relation in physics is in the form of an equation that both sides have the same dimension. If two sides of an equation have different dimensions, equality can be valid only in a special system of units. For example, suppose A and B, where A is length and B is surface area. For example, A is 10 meter and B is 10 square meter. If we write the quantities A and B in terms of centimeter and square centimeter, then A is 10 to the power 3 centimeter and B is equal to 10 to the power 5 centimeter square, which are no longer equal. If we want a physical relation to be valid in any unit system, both sides of equality should have the same dimension. Moreover, it's meaningless to say a dimensional quantity is small or large. For example, consider a length d1, which is 1 meter. This length can be written in terms of subatomic length unit, Fermi. 1 Fermi is 10 to the power minus 15 meter. So d1 is equal 10 to the power 15 Fermi. This length can be written also in light year. 1 light year is the distance that light travels in 1 year. It's the velocity of light, 3.10 to the power 8 meter per second times 3,600 times 24 hours times 360 days in each year. The result is approximately 10 to the power 16 meters. So d1 is equal to 10 to the power minus 16 light year. So 1 meter in a system of units has 10 to the power 15, and in another system of units it is 10 to the power minus 16. So it is meaningless to say that 1 meter is large or small. The numerical value assigned to this length will change upon changing system of units. It may have a very large or very small value. d1 is very large with respect to the subatomic length of order d2, which is 1 Fermi. d1 is much larger than d2, and it's very small relative to 1 light year. For example, d3, which is 1 light year, is 10 to the power 16 meters. d1 is much less than d3. Dividing two quantities of the same dimension give a dimensionless quantity, which is possible to be large or small. For example, pi 1, which is defined as the ratio of d1 over d2, is 10 to the power 15, much larger than 1, and p2 is equal d1 over d3 is 10 to the power minus 16. The largeness or smallness of these quantities is valid in any system of units. When we change the system of units, dimensional quantities will change, but a dimensionless quantity takes the same value in all system of units. Numerical values of d1, d2, and d3 in terms of different units, for example, centimeter, meter, or Fermi, or light year, are different, but pi 1 and pi 2 have the same value for all of these units. We can add or subtract quantities of the same dimension. We can multiply or divide some observables with the same or different dimensions. The dimension of result can be obtained by same operation.